In this video, we're going to continue from our previous video and calculate out the delta G of reaction at various temps using the actual info for the entropy and enthalpy at those temperatures. So this reaction, Haber-Bosch reaction, I have nitrogen, I have 3H2, all gas. They are in equilibrium with 2 NH3. We're going to solve the delta G at standard state. We're going to solve the delta G at 473, 673, and 873. To do it, I'm going to need some delta H and some delta S values. So first thing first, let's solve some delta S and delta H values. So here's a quick data table. Let's calculate out the delta H of reactions. Well, remember that our delta H of reaction is going to equal the sum of our products, so 2 times the ammonia, minus the sum of the reactants. So that's 3 times the hydrogen plus the nitrogen. At our standard state, well, that's 0 for the hydrogen, 0 for the nitrogen, and 45 times 2 for negative 91,880 joules per mole for delta H at standard temp. Go ahead and do this for 473 Kelvin, negative 38,739 times 2, minus 3 times the hydrogen, so minus 3 times 5118, and also subtract the nitrogen of 5161. We'll find that our delta H of reaction here is minus 97,993, and if we continue down through the other two temps, we'll get minus 100,773 and minus 100,404. For our entropy, same basic calculation, just using our entropy values. So we can find the entropy change for the reaction at 298, that is 2 times 192.77 minus 3 times 130.68 minus 191.9. Negative 198.4 joules per mole Kelvin. Do this for the whole table and we'll find the values of negative 216.7, negative 227.0, negative 232.1. So you can see because the enthalpy and entropy of the formation values have changed for each chemical, the enthalpy and entropy values for the reaction changes have altered as well. As our temp increases, we find that the enthalpy change of reaction is getting largely greater, and we find that the entropy change of reaction likewise is getting largely greater. Well, both of these are negative, so in our calculation of delta G is going to equal delta H minus T delta S, the greater our temperature becomes, we'll subtract a larger negative, we'll be adding, and if delta H is negative, we'll be adding onto a negative, making it more positive. Eventually, as this temperature goes up, our delta G is going to stop being favorable. Well, if we want to plug this in and calculate it out for each temperature, we can take our delta H for that temperature minus that temp times the S value to solve our delta G. And what we will find for each of those is that our delta G is negative 32757, so about 32 kilojoules per mole for standard state, which is what we would calculate using the standard state values normally. For the next one, we'll have negative 97,993 minus 473 times negative 216.7. Even though delta H has got a little bit larger, our entropy value got a little bit larger, and our temp got significantly larger. When they multiply together, this is going to subtract a great deal of negative from the entropy in the calculation. It's going to end up being more positive. In fact, this comes out at 4,506. At 673, the delta G comes out at positive 51,998. And at 873 Kelvin, comes out at 102,219. These would be in joules per mole. We see that as the temperature went up, the free energy got more and more positive. The reaction becomes less and less favorable. If we'd attempted one of these calculations without using the corrected values, like this one, let's just check at 473 using standard state. So in this case, we would be taking our negative 91,880 joules per mole for delta H, subtracting from that T delta S, but we're going to, instead of using the standard state 298, we would plug in the 473. And we try to use the standard state value for the entropy, minus 198.4. Had we used our standard state entropy and enthalpy values, the delta G we would calculate out at 473 would have equaled 1963. It would still be positive, but that is reasonably far off. It's less than half the actual value. If we tried using our standard states even further away, if we tried to just use our standard state values but plug in 873 for the temperature, we'd calculate out 81,323, off by 21,000 joules per mole. The use of the standard state values from our textbook for most data tables is very useful because that is where we do almost all of our normal benchtop reactions. Even if we heat it up, we don't tend to get too far away. Boiling water is only 373 Kelvin, so we wouldn't even gotten as far away as we did here in our second calculation, which means our air should be even smaller between those. The hottest you tend to get on a lab bench isn't too far away from the standard state, and so the air that we obtain isn't too great, but it is an air. If we truly want to know what a calculation should give us at a temp further and further away from standard state data table, we end up having to have data for those increased temps. This becomes very particularly important in industrial reactions where things are not done at room temp, like the synthesis of ammonia. The Haber-Bosch reaction is one of the most industrial important reactions on the planet. It's the only reason we have fertilizer for farmlands. Making ammonia is one of the most vitally important for human life reactions that we do in the modern world. But if we want to check what the air would do for us, well, let's zoom in here on 473. Let's do two versions. Let's do an accurate version. Let's do the approximation. What we're going to look at is we're going to look at the equilibrium in this reaction. Remember that the delta G is equal to the negative RT ln of K. If you know the free energy of a reaction, you can figure out what the equilibrium constant for that equilibrium reaction will be. So as nitrogen and hydrogen try to combine to make ammonia, how far towards the ammonia side will we get? Let's compare just how different 4,506 versus 1,963 really is in our K values. 4,506 joules per mole is going to equal negative 8.314 joules per mole Kelvin. Temp, well, we're saying this is 473 Kelvin, ln of K. Rearrange, solve for the ln of K. Negative 1.1458 is the ln of K. E to both sides. Our K value would be 0.318. So a fair amount of products, not dominated by products, but definitely not all reactants. If we wanted to do our approximation, where we were using our standard state values for something that is getting too far away, 1963 was what we would have calculated using standard states, but plugging in 473 Kelvin. Well, that would still equal negative RT, so negative 8.314 joules per mole Kelvin, 473 Kelvin that we're looking at, natural log of the equilibrium constant. In this case, we get negative 0.49917 is the ln of K, E to both sides. Our K value comes out at 0.607. Well, that's about twice as much. This would represent that we would make twice as much products over reactants as we did for the accurate value. If you're attempting to produce ammonia and you want to know how much you're producing, so you know how often you have to ship it to a container to cool it down, to collect it before sending the gases back into the main reactor, If you only have half as much as you thought you were going to have, your plant is not going to operate very well. And so if our equilibrium constant in reality is half what the approximation thought it was going to be, this is going to be a problem on an industrial scale. Often for our calculations, we're not too far away, and we're not terribly concerned with the fact that entropy and enthalpy do vary with temperature. But I wanted this video to highlight they do change, and that can affect our calculations. As soon as we're getting further away than standard room temp, this becomes a concern that can't be ignored.